can get some new information out of the picture then. And that is, it's a pretty important idea when you have the word fundamental in front of it. Sort of each branch of mathematics has its own fundamental theorem. When you get to calculus next year, you'll learn fundamental theorem of calculus. In Math 12, you'll learn the fundamental theorem of counting. Yes, there's a branch of math called counting, but it's not like 1, 2, 3, 4, quite as easy as you think. So the fundamental theorem of algebra is how is the degree of a polynomial related to the number of solutions? What do you think? So let's take a look at what we know already, okay? What kind of equation is this? What would you call it? Or what would you call the picture? Linear or a line, right? So let's just say this was the line x plus 1. Okay, now let's take a look at another thing that you're familiar with. Whoops.
There's 1, 0 when there's only one polynomial and there's two.
Okay, so what do you think? What do we have here? A parabola, which is an x squared. So maybe this is x squared minus, I don't know, 2. And then we just looked at some new graphs. And these were the cubics. Okay, and there could possibly be as many as 3 solutions. Now, one trick though, you'll notice, remember with parabolas, you could cheat and you could say, oh, haha, there's no solution. You're wrong, because this does not touch the axes. Or you could also do something like this and go like that and say, it's like a line. There's only one solution. So what we have to, yeah, that's right. There's going to be imaginary roots. But for us, we're not working with imaginary numbers. We're just working with the reals. So what we can say here is that, I'm going to need to make a little bit of space, so I have to erase this graph. What we can say is that the maximum number of roots, we can state, the number of roots, which is also known as a 0, of the polynomial must be less than or equal to the degree of the largest term. Okay, so for cubics, there can be at most 3. For squared terms, like x squared, there could be at most 2. So we know we don't need to look any more than, if we have a cubic, we don't need to find any more than 3 solutions. If it was a x to the 5th, there'd be no more than 5 solutions. Okay. Okay. Now, another thing, if I was to put in I know I'm running out of space here on this sheet, but even our cubic graphs, right? Here's an example where that cubic graph will have, thank you, but I'll restart later, 1, 2 solutions. So it's not because it's even or because it's odd, right? If I move this high enough up, I could make the cubic graph have only 1 solution. Okay. Can you think of anything else that you might be able to guarantee between even and odd numbered polynomials? It's actually on there. The picture's on there. Is there something you can say if you have an even numbered polynomial or if you have an odd numbered, like x to the 1 or x squared, even odd?
There has to be one solution for the odd number?
Yeah, that's right. For the odd numbers, there has to be at least 1 solution, but the even numbers does not have to have a solution. So there may not be a solution at all when we have an even number. And the reason the evens don't is the n behaviors are the same. On the left side here, it's going up, and on the right side, it's going up. But on the left side of this, it's going down, and on the right side, it's going up. So that the behaviors, we call those n behaviors. The n behavior is in the opposite way. It's got to cross through the axes at some point. Same thing here in the cubic. It's going up here, down here. That means at some point, it's going to have to cross the axes.
Excuse me?
Yes?
If the line is vertical, or no, I mean horizontal, that's not going to be a polynomial.
A horizontal line has this equation. That's a good point. So let's say it was y equals 5. Right? That is like x to the 0 term. Okay. Because x has disappeared. from there. So because it's x to the 0, technically, yes, you're correct, but it still obeys that law because it's x to the 0. Okay? Make sense?
What's that graph gonna be? Like the one that's to the left of the 3?
Which graph? This graph here?
Yeah. How's that gonna look like in equation?
In an equation, it means we won't be able to factor whatever roots were over on this side of the graph are imaginary numbers, and this one here would be positive. So it might factor to be something like this, like x, say, plus 3, and then the other factors, again, it's not something that we're going to have to do in our course, but maybe it'd be something like square root negative 2. And then the other factor would be something like x. I don't know exactly where they are, but this is why you don't actually see it touch the axes. It's because they're imaginary. It does factor, but it won't. Those are in that cruel world of university, as you'll see soon enough. Okay, so let's try one more here. Let's give this one a shot. How many x-intercepts does it have, and where will they be? Okay, so you can take a look. If you're still finishing up, you can catch up to what I've got. I found a root at 2. You may have found a different one, but that's the only one that's not a fraction. Then the other roots I end up getting by factoring is negative 3/2 and 1/2. So these would make up all of the possible factors, and I can see there are 3 solutions. So there are 3 x-intercepts. And their values are 2, negative 3/2, and 1/2. Okay, so it's important for you again to realize that the values you're finding are the x-intercepts on the graph. So as long as you make that connection between the two, then you're in good shape. We won't look at another one that does the same thing.